maintenant,
which I'll try to look at on Friday. So we get PDT fractionation, PDT continuous versus pulse growth. This I've never thought of before, but it's quite interesting, which is PDT and nutrition. I'm just trying to find some stuff on the internet at the moment, see if I can see anything sensible on that. Two photon PDT. Either two photon single wavelengths or two photon two wavelength and multi-photon PDT. So if anyone wants to add anything, we'll maybe at the end come back and extend the list. Okay, so just to finish off the second lecture, so I talked just to be about the biology of PDT and photophysics and photochemistry, but mainly about the biology, and just to remind ourselves that you can kill cells directly, you can kill tissue by vascular injury, and you can also have inflammatory or immune effects. So I wanted just to wanted to try to pull this together and look at what, at least for tumor treatment, is the end result of this, which is to reduce tumor necrosis. So here are just some examples of tissue necrosis with PDT. So in this case here is a tumor. This is tumor in the esophagus, treated with photocrypt. So we see the large tumor before treatment, and then this is 1 or 2 days after treatment. And you see essentially you cause necrosis throughout this whole volume, and then within a few days this comes off and the tissue heals. Actually, just as a clinical comment, in the 1980s when people first started doing this for lung, a couple of people, well, one person at least was killed, a patient, because it was not realized that you produce this hard necrotic mass for a few days, and in the lung that actually blocked breathing. So now for lung PDT like this, you do the treatment, and the next day go in and remove the dead tissue. It's called a toilet bronchoscopy. Here is brain tissue, normal brain tissue treated with various photosensitizers, and again you can cause these regions of necrosis. Here's skin treated with BPD, benzoporphin derivative, and again you see the different light doses. This is 50 joules per square centimeter, 100, 200. So you see you produce this massive necrosis. And here's a liver section with the light coming from the surface, and you see this region of necrosis produced by H&E. Oh, this is a stain, factor 8, which stands for vasculature. So you see the effects on the tissue. Now, if you're going to treat a tumor like this, obviously it's good if you can produce the necrosis throughout the tumor, but not damage the underlying tissue, because otherwise you make a hole in the esophagus, and that has been a clinical problem. Or even if you do not make a hole, you may cause damage and the esophagus gets strictured, which, for example, is a problem for subsequent nutrition. We'll talk about on Friday. So one of the observations made a number of years ago with PDT by many people, clinically and also in animal models, is that the necrosis or other responses is the same as true perhaps for apoptosis. The necrosis often has a very sharp boundary. So if we look at this situation again, this is liver tissue with the light coming in from this direction, and you see this animal has been injected with a blue dye after treatment, and you see the dye is excluded from this region. And the surprising thing is that this is fairly sharply bounded. I say surprising because you have light coming in here, and the light is absorbed exponentially. So you might expect that you would see a gradient of damage throughout it. So more damage at the surface, less. But you would see a continuous rate of damage. Whereas what seems to happen is that you have damage and then no damage. That's very nice as long as you can make this line in the right place. If you make it too shallow, you undertreat. If you make it too deep, you overtreat. And so the question is, why is this a very sharp line? If you do the same experiment, for example, with radiation, you cannot find this sharp line. You find a gradient of damage. So the theory for this is that it takes a certain number of molecules of the single oxygen per gram of tissue to produce this specific effect. And that if you have more than this number of molecules, you will produce the effect, for example, necrosis. If it's less than this, either you produce no damage or the damage can be repaired. And so this sharp boundary happens because of that. So this is like a step process. So here we have enough oxygen, singlet oxygen, damage, you go below a certain amount, and damage. And it's possible a number of people, including the group here, have done experiments where you measure the amount of drug at this level, you measure the amount of light reaching this level, maybe the amount of oxygen also, and you can calculate how many photons, how many light photons you need to observe by the photosensitizer per gram of tissue, and it turns out to be about 10 to the 19. So to kill 1 gram of tissue here requires about 10 to the 19 photons to be absorbed by the photosensitizer. Not by the rest of the tissue, by the photosensitizer. This has a funny unit. It's called an Einstein of photons. It's kind of nice for this year. So 1 Einstein of photons is 10 to the 19 photons. You never hear that term anywhere else. It's a nice term. We've done some experiments in which we are able to measure the amount of singlet oxygen required to kill cells, and to take the cell survival down to the 1 upon E, or 37%, takes about 10 to the 7. These are ballpark figures. About 10 to the 7 molecules of singlet oxygen to cause 30%, 37% killing. So you might think, you then ask the question, what fraction of cells in the tissue must be killed in order to produce necrosis? No one really has answered that question, but you might think you have to kill 99% or 99.9%. So maybe you have to give 10 times the 1 upon E level, so maybe you need 10 to the 8 molecules of singlet oxygen per cell. And if you compare these values, you're about right. Makes some sense. Within a factor of 10 or so. So if it looks as if this idea that the threshold is because you must produce a certain concentration of singlet oxygen before you get the effect, correct? You need to think about that a little, because one of the questions that's been raised is, over what time do you produce that thing with oxygen? So let me make the analogy. If I take 1 aspirin per day, what's aspirin? So 1 aspirin per day, will I die?
Probably not.
Hopefully not. I hope not, because I do take 1 aspirin per day. If I take a bottle of aspirin, I die. Probability of dying. So it's not really understood. If we give this number of thing with oxygen, you have to have it all at once, within 1 minute, 10 minutes, 1 day, etc. So no one has really looked at that, and it's an area for interesting research. Now, this is a nice response, because really in the region of treatment, the necrosis is very uniform. And in practice for tumors, that's often not the case, because in different parts of tumor you have different oxygen levels, different amount of blood vessels, so you have different levels of photosensitizer, and so on. So that in tumors, it's not so obvious that you have a specific value of the threshold. And just to illustrate that, one of the things that we've done recently in our studies in PDT of the prostate is as follows. So let me explain what happens here. So this is a cross-section of the prostate. And the prostate has been treated with photodynamic therapy. I'll show in the seminar tomorrow by putting optical fibers into the prostate. That's where all the guys cross their legs. Put optical fibers into the prostate. And we give the treatment. And the intention is to treat the whole prostate. But an example in this patient, if we then do a magnetic resonance image after, and this is superimposed, you see this region of dark here is a region of necrosis produced, and there's another region of necrosis here, and another region of necrosis here. But we've treated the whole prostate. And just obtained this patchy necrosis for this particular patient. Now this is still a clinical trial, so still developing. But what does that teach us? Well, what we can do is we are able to calculate the PDT dose at every point throughout this prostate, because we measure the light and can reconstruct the whole of the distribution. And so at every point along this boundary of necrosis, we're able to calculate the PDT threshold. And then if you plot the PDT threshold distribution, you find it varies by 100. So within this single organ, it is true that there is a threshold value, but in fact the threshold varies by a factor of 10 or a factor of 100. You can say that this is less than 100.
But certainly it's not the case for like liver, where it lines well different.
Yeah. So it looks as if, so you might think this is surprising. These patients actually are patients who've had previous radiation. So previous radiation completely changes, for example, the vasculature, and this is a vascularly targeted drug. So what probably we're looking here is a reflection of the altered microvascular distribution caused by the previous radiation. The details of that don't matter. I just wanted to point out that it is starting to be possible by combining imaging with dosimetry, detailed dosimetry. It's becoming possible to actually get some idea of the true threshold, not just of a tissue on average, but within a tissue and how much it varies. So that's probably useful information.
Well, maybe I should not ask this, but how is the drug distribution in this?
No idea. No idea.
Met the synthesizer concentration, light distribution.
Yeah. So we are assuming that the drug concentration is uniform because we have no way to measure. Because this is not a fluorescent drug. So that's a big challenge. We could take many biopsies and extract the drug and measure it, but this is a patient, so we can.
Yeah, no, I understand.
Yeah.
So it's a kind of, I'm sorry, but it's not then, it's a threshold, but it's a threshold histogram that still doesn't have the information about the drugs.
No, so
locally, that may be a result.
So this distribution could be a result of, it's not the result of the light, because we know that, that's measured. It could be variations in drug, it could be variations in oxygen, it could be variations in the cell, you know, in the prostate there is glandular tissue, there is connective tissue. A big expectation would be, the most optimistic interpretation is that this is a tumor and the rest is a normal prostate. That's probably not true. But there's a number of factors here. And now it becomes a challenge. It's probably going to be impossible to measure all these factors. So what do we do to make this treatment more successful? Do you just keep increasing the amount of drug, increasing the amount of light? You're concerned here because the rectum is here. So you can just keep increasing indefinitely. But it's perhaps the most challenging area for PDT because you have a situation where you want to treat the whole of the prostate for cure. So you have to be very aggressive, but you have the rectum close by, you have the urethra, you have the bladder sphincter, you have the erectile nerves, nerve bundles, so there's a lot of normal structures that you can damage here. So this requires very, very detailed treatment planning and measurement. Fortunately, most treatments are much simpler than that. So let me switch to the second lecture. So for the rest of the day, I'm going to talk about technologies and some clinical applications. So what about the light source? What sort of light sources do you need to do PDT clinically? I'm talking now really about clinical requirements. So, as we saw yesterday, you need the wavelength to match the activation spectrum of the photosensitizer. Be a little careful here, because in some photosensitizers, the action spectrum in vivo is not the same as the absorption spectrum in solution. So you have to check that. You have enough power to generate the reaction, the light has to be deliverable, and it has to be safe, reliable, cost-effective, available, work in the clinical environment, etc. So all those practical issues. The light source requirements actually are pretty challenging. I said yesterday that PDT is an energy inefficient process. So if we take, for example, a surface treatment or an interstitial treatment, and let's say that you need 100 joules per square centimeter delivered in 15 minutes, so to the surface. And that's typical, say, for a skin tumor. That means you need 0.1 watts per square centimeter. So if you're treating a 5 centimeter by 5 centimeter area, that means you need 2.5 watts. That's quite a lot of light. 2.5 watts at the specific wavelength. Similarly, if you have the interstitial case, Let's say you have a 3 centimeter by 3 centimeter by 3 centimeter volume, something like, say, the prostate, you would also need 2.5 watts. So in general, at least for cancer treatments, it's much less for infection, for example, but for cancer treatments, you need a few watts of light at the right wavelength, delivered in the right way. So there are several choices. You can use lasers, LEDs, or filtered lamps. And the advantages, the main advantages of lasers are that you can couple them very efficiently into single optical fibers. So if you want to do interstitial treatment, for example, it's very difficult to get, almost impossible to get reasonable amount of light from a lamp. It may start to be possible to get enough light from an LED delivered into an optical fiber, but still that's challenging. Big advantage of LEDs is that they are very flexible configuration. I'll show you some slides to illustrate that. And the big advantage of filtered lamps is that they have a broad spectrum, so you can put a filter in and easily change the spectrum if you want to go from one sensitizer to another. If you look at the history of the development of light sources for PDT, this is the 70s and 80s. So I showed you this yesterday, this slide from Roswell Park of a scientific argon pump dye laser in an operating theater. The last time I was in Brazil at Univac, we did an experiment in the lab with one of these systems, and in the middle of the experiment, the tube flew off from the dye laser, and dye sprayed everywhere, including all over us. So that's not good. That's very carcinogenic, that stuff, and certainly not good in a so we all had to go to the washroom and stuff ourselves. People look very purple for a few days.
Well, they glow in the dark if you...
Yeah, they glow in the dark. This original technology, a number of companies tried to make this better for the clinical environment by putting it in a nice box. But the same core technology was inside, and it was very expensive. Good power, you could get several watts, tunable, which was a big advantage. Reliability was terrible, and it was very unuser-friendly. This is an example of this actually was a system that we used clinically, in which, to make this system more compact, they took the argon laser and had it vertical on an angle, coming into the dye laser at the top, which was a nightmare for optical alignment. So this is a system we're using in the operating theater. This is me when my hair was darker. A number of groups use copper or gold vapor lasers, these huge monsters, which have a ceramic tube, and you feed gold into it, and it reaches very high temperature, it's vaporized, and lasers. So you have to keep putting gold into this. It's like children, you have to supply gold. Very high power, but a big beam. People try, for example, were able, without doing any collimation, to deliver light into multiple fibers simultaneously. We're very popular in Australia. There's a company in Australia that did these, and a company in England, but they're very large, more reliable than this, but still difficult technology. In the early 90s, the KTP pump dye laser was introduced. So this was a frequency doubled neodymium YAG laser, so 1064 doubled to 532. So this is solid state. It's still required to dye laser, but you see it's starting to look more clinical. Good power, still tunable, pretty reliable. The solid state part pretty reliable, still very expensive, and so-so user-friendly. One of the advantages was that this could be used as a green laser by itself for surgery. And so the different clinical groups could use this as a surgical laser and then connect it to the dial laser to the PDT. We still use one of these, actually, that's now 15 years old, so pretty reliable. Although I have to admit we haven't tried to change the wavelength for years, so I still don't know how easy it really is to tune them. In the mid-90s or so, diode lasers were introduced. You see these various systems here. Compact, optical fiber delivery, don't require water cooling. So reasonable power, not as much as you could get from the big frame lasers, but 2 or 3 watts. Big disadvantage is not tunable, and still relatively expensive. This is about $50,000. So if you need one of these for each photosensitizer, then this becomes expensive again. So then a disadvantage, very user-friendly and very reliable. So these are really the state of the art at the present time for laser-based PDT. LEDs also started to appear in the mid-1990s. This just shows various examples. This is a large array developed to actually do PDT of bags of blood for blood purging to kill HIV virus and also hepatitis B virus. And a number of services, for instance, New York for a number of years used PDT for purging of blood in the blood supply. And I think it's France, in some areas of France, they still use this. Not used, at least in North America now, because it's an expensive way to do it. And there are also concerns because you have to mix the photosensitizer with the blood, and then you have to re-inject. So there's a concern about toxicity. Here's a system developed for clinical surface PDT. Little LED here, developed by a company in England for oral cavity. So just put this into the mouth and shine it on the gums or the cheek or the tongue. So quite nice technology. So you see the flexibility in the arrangement. The company in Seattle, the US, has developed an interstitial LED array. So this is a little fiber-like device, a couple of millimeters in diameter, that has individual LEDs all the way along. And so you have a line source that you can put into tumor or use endoscopically. Very nice for some applications. The limitation on this, and you see it's a nice compact unit, the limitation on this is that these LEDs produce quite a lot of heat. And so unless you have cooling, active cooling here, since these are inside the tissue, this limits the power to about 25 milliwatts per centimeter of length. So it makes the treatments quite long. Now, if you talk to the people at Life Sciences, they say, well, that's an advantage because we get some different mechanism of selectivity by giving the treatment over a long time instead of a short time. Maybe that's true. But there would be interest in, and I think Life Sciences are trying to make these now incorporating cooling. But of course, there's a problem because you want to have a very narrow fiber. So how do you cool a long narrow fiber? But that nice technology. Developed by neurosurgeon. Interesting. Called James Chang. Filtered lamps. Lots of different types. So basically you have broad spectrum, and you can use filter to select the region of interest. Of course, the problem with this broad spectrum is that you are using only a fraction of the power for any given filter, so a lot of the power is wasted. So although that you can have very high output, the usable output may be much less. Lamps are still useful for some purposes. For example, this is a a system that we built years ago, which uses just fluorescent tubes with filters over them in a bank. And inside here is a flask for tissue culture. So you can irradiate a whole tissue culture flask at one time. You can build this for $200. So lamps are still somewhat useful if you want large areas, for example. And of course, lamps are used in Cuba. This is the lamp that was developed for treatment of actinic keratosis. Remember the sun-damaged skin in the head and scalp. So it's a bank of U-shaped fluorescent lamps that are blue filtered. In this case, blue light is used because the condition is the disease is very superficial. So you do not want to have heat penetration. You use red light, you do a lot of damage. So here you use blue light. This is very clinical. It costs about $2,000. Just not too bad. Just switches on and off. Very reliable. It's actually, if you want to treat a large area, this is a pretty nice technological solution. So, although generally lamps are dying out and being replaced by LEDs, there are some circumstances where it's still probably competitive. People have used lamps, for example, in treatment of ovarian cancer, where you want to irradiate the whole of the abdomen. So you basically, at laparoscopy, you open up the abdomen, all the surfaces are covered with cancer, so you want to treat all the surfaces. Now you have hundreds of square centimeters of surface, so you need raw power. And in fact, there's a group in Philadelphia do this with 2 argon pump dilators blasting away, and it still takes 2 hours to do the treatment. What they do, in fact, is also use a lamp, and this is a little gruesome, but there's disease all over the intestines, so they pull out the intestines, and they have a lamp that closes over, and they cool the intestines through the lamp. So you need a lot of light for this. And this is an example of using lamps placed inside the abdominal cavity. Again, you have to think here, this is a very difficult situation because you have a very complex surface, and it's important to treat the whole of the surface. People often have tried filling the abdomen with intralipid, which is a light scattering material, so that you have a whole light scatter medium inside. Yeah.
Will you have any case of cure?
With the ovarian?
Yes.
So that's been a difficult issue. There was a trial done 10 years ago at National Institutes of Health in Washington, which looked very positive. And the group in Pennsylvania have been doing a follow-up trial for the last 5 years that's completely negative. They can't get it to work anymore. And it's the same guy. The Eli Gladstein moved from Washington to Philadelphia, continued the treatment, and he can't make it work anymore. And no one understands why. So there's a real, everyone's a little stuck at the moment. Because it should work. If it worked, it would be very important technique for that problem. And we don't understand why it's just no longer working. What has changed? So maybe you have to have a different drug. Maybe there oxygenation, maybe you have to oxygenate the fluid. It's not clear. Sometimes, it's not completely negative. There are some patients who the response is good, but they cannot reproduce the original result.
What about other organs?
Within the,
Yes.
well, the idea is that you treat the whole of the surface of the abdomen, the whole of the intestinal tract, the whole of the peritoneal bed, the all surfaces.
But do we have any really good case that
There are individual cases
Yeah.
that are very good, but the whole process seems to be very difficult to reproduce. Here's a nice map with I said that you cannot deliver light efficiently from a lamp into an optical fiber, but you can deliver light into a fiber bundle, or in this case, a liquid light guide. So if you can accept maybe a centimeter diameter bundle, then you can use this and deliver light quite nicely. One point you have to be careful about is that if you take a laser and you find that for a particular tissue you require, say, 100 joules per square centimeter, and let's say it's for photoframe 630 nanometers. So 630 nanometers, you give 100 joules per square centimeter to get a particular response. If you take an LED or a filtered lamp and give 100 joules per square centimeter, you will not get the same response. And the reason is that if this is the photosensitizer peak, so this is the absorption spectrum, then a laser centered on this peak is maximally effective. Whereas if we have, say, an LED that has a distribution of output, typically this may be 25 nanometers wide, then obviously there is not the same effectiveness of this light at this wavelength as there is at this wavelength. So generally for LEDs and for filtered lamps, you find that the output power, the effective output power, is about half of the output power of a laser at the equivalent central wavelength. So it usually requires about twice as much light with an LED source as a laser source at the central wavelength.
Yeah, but that doesn't mean that you're going to have half of the effect. Because a shorter wavelength may go a little deeper.
Yeah, and so this is just the photophysical, and then you have to fold this in with the tissue properties and so on. But actually, empirically, for example, people who've done LED treatments or lamp treatments compared with lasers find they need about twice as much light with the LED and the laser.
We found we can invest 10% of the audience the same result for the depth of necrosis in liver.
Yeah, liver may be a little exceptional because the absorption of liver is so high that you may get a lot of effect at narrowing.
We use these new LEDs which is narrow.
Yeah. The narrower it is, the better.
Yeah. It's only like 10 to 15 nanometers.
Yeah. So the commonly available LEDs at say 25 nanometers have about 50%. You know, it may be 30% or 20, but you have to adjust. You cannot just use the same power and assume that it will work in the same way.
Information.
Yeah. Delivery systems. So this is Paul Mueller, who's a neurosurgeon that we work with, fooling around, showing that you can use an optical fiber to deliver light. Nice slide. You can deliver light into optical fiber. And he is one of our volunteers receiving optical fiber treatment. So you produce the light, now you have to deliver it. So you have to couple the light with high efficiency, and you have to match the distribution to the target tissue geometry. So if you have, in theory, a square tumor, you've got to have a square distribution of light. And you have to minimize the exposure to the non-target tissues. And also, these delivery systems have to be safe, reliable, cost-effective, etc. So if you look at the different geometries of delivery, you can have superficial, interstitial. Those could be point sources, interstitial, or line sources. It could be multiple interstitial. endoscopic, where the fiber goes into the endoscope. Can also be done from the surface, or it can be interstitial, or it can be distributed like this. And you can oppose surface endocavitary, either by having a point source within the cavity, or by having just a cut fiber and fill in the cavity with the light scattering medium. So this, for example, would be in the bladder. This could be, we use this, for example, in the brain, after we take the brain tumor out to radiate the whole surface. And then, of course, the exception to this is in ophthalmology, where you're delivering the light through the pupil. From laser sources, optical fiber delivery is optimal, and this just shows a couple of examples. Typically, you get greater than 90% coupling into single fibers. And over the years, a number of different optical fiber configurations have been made. You can take optical fibers with a little lens in front to produce a very uniform beam. You can have a scattering tip, which produces a sphere of light, and you can have a diffusing fiber that produces essentially a sausage of light. And this just shows one of those fibers going inside an endoscope if you wanted, for example. So this situation with one of these fibers would be this type of treatment. Typically, you want these to have a nice uniform distribution along the length, and you can plot the distribution of light spatially around the fibers. This just shows examples of different lengths. These are commercially available. They're about $400 each from the commercial supplier, so if you can find a cheaper way to make them, that's real good.
Why are these so expensive?
Why are they so expensive?
Well, they're actually not that easy to make. They're not that easy to make
With very tight specifications.
You have to take the fiber, you strip the cladding, you have to coat the cladding, and you have to re-clad with a transparent cladding so that it's just still strong. You have to, in some cases, you have to add a sharp tip so that you can go into the tissue. And there's a lot of work in making one of those. I'll show you tomorrow an alternative technology that we've developed that might be much cheaper. We need a few diffusers here. Yeah. If you're making them for the lab, it's easy. I mean, the real cost here is to make these clinically approved devices. You know, these have to be approved by the FDA. That means they have to have a certain quality of reprint. You know, you have to have certain quality standards. They're still too expensive, but I suspect if there was high volume and some competition, it might come down to $100, but it's not going to come down to $10 as technology. And often they're single use. Here's an example of multiple optical fibers going, in this case, into the brain. So we have the patient here with a template onto the brain, and all these optical fibers coming in, essentially to give a light distribution throughout the whole volume. As well as the diffusing fibers, a number of groups have developed balloon devices. So here's a balloon device for the esophagus, so that this balloon collapses, goes through the endoscope instrument channel, and then is inflated with air or with water, and then once it's inflated, you insert a diffusing fiber through the center, and these come in different lengths. You can shield one side if you just want to treat one side, for example, of the esophagus. Again, these are commercially available. The group in Switzerland did esophageal treatment with a different technique in which they made a rigid device that goes into the esophagus with the diffusor already built into it.
Here's another example of balloon, in this case from our own lab, where we're doing irradiation in the brain after surgery. So the tumor is removed and we irradiate the cavity. And so this is done by essentially taking a balloon, filling that balloon with intralipid, which is a light-scattering material. Maybe comment on nutrition. You know, intralipid is a nutritional material. You give it for people who are not able to take nutrition. So now here's an application of nutrition to PDC. I just thought of that. So the optical fiber comes down into the center, and the fluid here scatters the light many times so that there's uniform distribution throughout the surface. So this is put into the brain and then inflated with intralipid. Here's an example of a balloon device that was developed for treating in the uterus. And so here we have the uterine canal. So this like an umbrella. Well, there's two types here. Sorry, the balloon here goes through the canal into the uterus and is then inflated. Or there's an alternative technology which is multiple optical fibers that are collapsed like an umbrella, go in the canal and are opened up to try to shape the distribution to the volume that you're trying. In ophthalmology, for retinal disease, this is fairly straightforward for most patients. It's a simple ocular lens, so that the light is just magnified to the particular area in the retina that you want to treat, and this is usually just done through a fundus camera. So this is fairly straightforward, at least as a standalone. With LEDs, you can, rather than having the light source and then the delivery system, you can put the LED right into the tissue. I showed you the example of the interstitial. Here's an example of an LED. Instead of, in this case, we have the laser. This is a KTP laser. We have the laser delivering light to an optical fiber into the balloon. So another group has taken the same device with the balloon, but now the LED is inside here. And instead of an optical fiber coming down this channel, you have an electrical wire. Here's a couple of examples of lamps. I showed you this one already. Here's an example of an arc lamp with fiber delivery, fiber bundle of light guide delivery into an applicator, and the group here also has similar technology. So, in general, there are a number of different core technologies for light generation, with lasers still being used where you have to deliver the light endoscopically or interstitially. In general, LEDs are taking over for all the other applications. And you notice from those different types of delivery device that there is some core delivery technology, such as optical fibers, but usually the delivery system has to be specifically designed for the application. If you want to do intrauterine, if you want to do intercavitary, etc., you have to design an applicator for each particular application. That's good and it's bad. It's good because you can set up a company making these devices. It's bad because it's expensive, because then you need to design a device and test it and have it approved for every application. So you cannot get a generic approval for all types of delivery devices. A few words about dosimetry. So I showed you yesterday the energy diagram, and one way to do dosimetry is that you measure each of these, the light, the sensitizer, and the oxygen, and you try to combine the measurements into a prediction. all you can measure the thing with oxygen directly. So for light dosimetry, we start with light dosimetry. You can take the same idea of a scattering fiber, but now instead of using that to deliver the light, you can use it to detect the light. So here we have a scattering tip, and now this can be put into tissue. I'll show you an example here of one of these detectors into the brain of the volunteer. Into the brain. And you're able to actually map out in some detail the distribution of light, even within something as small as a rat brain. In order to do this, you have to make this, if you do this with just a fiber, you just take an optical fiber and put it in, you get the wrong answer. And the reason is that if you take just a cut, if you take this ball off, then you can put a detector here and measure the light, but you'll only measure the light that is within the acceptance angle of the fiber. So light is coming from this direction will not be detected. So the idea of this tip is to make the light equally probable to go down the fiber by having it multiply scattered inside here. So it's a matter of which direction the light hits, it gets multiply scattered, randomized in the tip, and a certain fraction goes and is detected.
How is the surface stuff? Is it a light surface?
Yeah, people have done different things. I mean, this is you can do it by taking a little sphere of epoxy with some mixed with some titanium dioxide, and then you just make a little tip on the end. The more recent ones, if you buy them commercially now, you don't have this sphere. They simply take the fiber and they strip off the last millimeter and then coat the millimeter with the scattering material. Not quite so good as this, but pretty good.
Yeah, I've seen like people just stick some aluminum powder.
Yeah,
at the very end.
very end. Yeah, people do that. Yeah.
So that you think works fine.
It's okay. I mean, these give you very good isotropy. The simple stripped coated ones are not quite so good. They're not so efficient in the backward direction, but for many purposes. You can use diodes for surface or intracavitary treatment. For example, in the case of the ovarian cancer patients, these diodes are actually sutured into the cavity. And as the light is moved around, you try to deliver the same amount of light to all points. These have been used, for example, in the esophagus. You can attach these probes to the balloon, so that can go down into the esophagus, and you can measure the surface dose of light. You try to standardize that between patients. This was a nice system developed in the Netherlands for bladder, where through the cystoscope, you had first of all a diffusing tip to deliver the light, and then this is very clear here, this again sort of cage thing here, a wire cage, and these are 3 catheters, and one of these diffusing optical fibers is inside each catheter, and then it comes out and it's connected to the symmetry device. Again, the attempt there was to be able to adjust the position of the light source so that you get uniform irradiation of the bladder. This is examples of using these interstitial fibers in our lab with prostate cancer in an animal model. So you can put lots of these fibers in, and people have done this clinically. Here is a patient in Switzerland with cancer of the head and neck. Where the treatment is endoscopic, but then one of these optical fiber probes is pushed through the tissue, and the light is measured as a function of position. Again, just to try to standardize things between patients. So the patient's lying here, a template is placed, is fixed in the patient, an ultrasound probe is put in the rectum, the source fibers are positioned through the template, and you can image the position of the fibers by the ultrasound, so you make sure they're going to the right place. And then we also have a number of detector fibers placed within the prostate, placed in the rectum, placed in the urethra to measure the distribution of light. And that all comes to a multi-channel detector that's computer online. And as an example of what you can do with that sort of system, here is the ultrasound cross-sectional image showing the various fibers, the detector fibers and the light delivery fibers. As indicated here, so these stars are treatment fibers. So in this case, this patient, there were 5 treatment fibers, and then there were these detector fibers, these 3 positions, and also one in the urethra. And so it's possible then to, for example, turn this light source on and measure here, here, here. Then turn this light source on, measure here, here, turn this light source on, etc. And so you can map out the light distribution.
Don't you do like in brachytherapy? So you try to put the intensity,
so
overall illumination.
Right. So this is what happens is that the treatment is pre-planned. So we plan the position of these fibers and the amount of light to give a uniform distribution. But then we have to check that and confirm that with the individual patient. You can, from that, for example, if we have light coming out here, then we measure here, here, and here. We have measurements at 3 different distances. And so you can fit these data to diffusion theory model and calculate the absorption and the scattering coefficients. In other words, you can get the optical properties of the tissues. And it turns out that this is a plot of the light as predicted by the treatment planning versus the measure. And you see it is correlated, but there's a lot of scatter from patient to patient. So that's just biological variability. And you can measure also, this is done online, so you can actually measure the light at some point A, B, and C during the treatment. And in this case, you see, in fact, the light is decreasing generally during the treatment, possibly due to changes in the blood flow. The treatment may be causing some vascular response, more blood coming into the tissue, and therefore more attenuation of the light. So you can think that you're delivering a certain amount of light, but by the end of the treatment, you may be delivering quite a difference. So it's useful to have these measurements.
This is did I lost this footage? What the decrease is coming from?
Well, there are several possible explanations. The simplest is that this is a vascularly targeted drug. And so the simplest explanation is that there's an alteration in the vasculature. It's supposed to be closing down, but there may be a transit, a temporary phase of vascular dilation happening in this case, and you basically then are attenuating the light because of the increased blood volume. We don't see this in every patient, so it's important to measure this on a patient-by-patient basis. Okay. Just quickly, some clinical applications. As I said, if anyone is interested in particular clinical applications, let's add it to the list, and I'll try to cover it on Friday. So just let me know at the end here. I showed you this yesterday, just the list of different applications that people have looked at. I thought it would be useful just to give you an update of the current status of PDT. This for the approval. So Photodynamic is approved for lung, GI, bladder, cervix, some early stage, some late stage, Barrett's esophagus, which is a pre-malignant condition, and it has approvals in Canada, US, Europe, and Japan. Now, this does not mean that all of these treatments are approved in all of these countries. So, for instance, in Japan, the approval is for early stage cancer of any whole organ. Because that's the way the Japanese approval system works. You can get it based on that sort of general description. That's impossible in the US. You have to say which organ you're treating and at what stage of the disease. So that in the US, for example, early lung cancer is approved and obstructing GI cancer. So each one of these approvals requires clinical trials. That's why this is so expensive.
Yesterday, or before yesterday, I thought you had included the skin cancer in some
skin cancer, to my knowledge, is not government approved anywhere. So actinic keratosis is approved, but as far as I know, skin cancer is not. Now, this slide is not absolutely up to date, so you might want to check that. It's possible, by the way, that maybe skin cancer is approved in some countries. This is not absolutely complete. BPE is approved for age-related macular degeneration. Actually, this should now include other countries also. It's approved in Europe, in Canada, and in many countries in the world. This was Torin E6 was a drug that originally came out of Japan, and it has an approval in Japan. It's currently the drug is being used by the company in Seattle. MTHPC was an interesting case. So MTHPC is the most powerful drug ever used clinically for PDT. You need, typically with photoprin, you need 2 milligrams per kilogram. With MTHPC, 0.2. It seems to be 10 times more potent than other drugs. No one understands why. This was originally developed by a group in London, England, commercialized by a company in Britain, and they decided to go for FDA approval for head and neck cancer. And they spent tens of billions of dollars on clinical trials for MTHPC for head and neck cancer, and they went to the FDA. The FDA said, your tumor response results are excellent, the toxicity is unacceptable. So the company went bankrupt.
But is it true?
Yeah. Because this was such a powerful drug, and they were in the head and neck, so there's lots of blood vessels, and this is a pretty complicated area to use a very potent drug on. Lots of people thought they were crazy to go for that application, but they went for it. So what's happened is that the UK company went bankrupt. The drug was bought by a group of venture capital people in Singapore for £60 million, which means $100 million. They had it for about 6 months and then sold it to a German company. So now BioLitech owns MTHPC. And no one knows quite what they're going to do with it.
So this is very powerful.
Very powerful. It has one approval in Europe for one specific condition. It's extremely powerful, and that's great, but it also means it can be very dangerous, which is where they have the problem with it. There have been studies, for example, with this in prostate and various other. Because there are so many clinical applications and it's such a rapidly changing, I thought it was not useful to try to go through a great list. So I hope is this readable on these printouts? Is it readable? If not, we can do it. Okay. So I recommend that you just go to these websites and to get it out. There's some of the websites are very nice. They include basic information, PDT, as well as the clinical data, and lots of them have references and so on. So this is a good starting point if you want to create an information database for PDT. Just to flick quickly through some approved treatments, cancer. Potentially, PDT can be used in palliation for obstructing or metastatic tumors, for control of early or localized disease, or prevention in the case of Barrett's. It can be used as primary or recurrent cancer, as a standalone treatment, or as an adjuvant. I showed you this example of the of obstructing esophageal cancer. And clinically, these patients are unable to swallow, and so the clinical endpoint for these patients is not survival because they're not cured, it's a quality of life. So this is a quality of life measure, in other words, the amount of dysphagia, how difficult it is for the patient to swallow food, and so there's a significant improvement in dysphagia score with PDT. Here's an example in late-stage lung cancer. So here's a patient with obstructing tumor in one of the lobes of the lung. So you see on the X-ray, there's basically this is air, and this is completely obstructed. So there's no air going into this lobe of the lung. Optical fiber, treat, produce necrosis, go in, take out the necrotic tissue, and you basically open up. Again, palliation.
There is an interesting application for using cheese, when they put stents on glandular tissue.
Yeah.
You know that.
Yeah.
That's it's been a very important application.
Yeah. So, for example, in the esophagus also, what people are talking about doing is you once you've opened it up, you then put a stent, which gives you the mechanical stability. The tumor keeps growing, but you can go in and keep killing
But for bronchus,
and for bronchus also.
you put a stent, and then because there are a lot of motion, you grow not the tumor, so you grow
Granulation. Response of the placement.
Oh.
So,
And there's a
They have been able to.
And is the granulation tissues responsive? Kidney to DNA? Oh, okay, I didn't know that. Has that been done clinically?
In the United States.
I showed you this before. It's just the treatment for cure. So this was the previous was palliation. This is cure. This is 5 years later, no disease. PDT is the only treatment. And here's some data. This is now quite old, but just to show you an example, this is in early stage lung cancer. This is the data for which the treatment was approved in Japan. 34 patients with early stage lung cancer, 85% complete response rate, and if you include partial response rates, over 90%. The later the stage of the disease, the worse the response rate, of course, but nevertheless. Brain, this is our own work in PDT for brain tumors, showing that the higher dose is better than the lower dose. Barrett's, probably people don't know what Barrett's is. How many people have heartburn? What's the president for heartburn? Too much food late at night.
Too much feijoada.
Too much feijoada. What's that called? When you have acid reflux? Reflux. Okay. Okay. So if you have reflux, chronic over long periods, then the surface, the mucosa of the esophagus becomes transformed, and instead of being this nice white squamous tissue, starts to look like the lining of the stomach, of the colon is columnar. This is not malignant, but there is a 50 to 100 times greater probability of developing dysplasia and cancer if you have this condition. And so PDT is, the idea of PDT here would be to treat this, eliminate the abnormal glucosa, allow the normal glucosa to repopulate, and so reduce the risk of developing cancer with prophylactic. This is a study published on the basis for last year's approval of PDT for this condition. So these are patients with dysplasia, in other words, regions of pre-malignancy within the esophagus. And so you see that, for instance, before PDT, there were 73 patients had high-grade dysplasia, and after PDT, there were only 7 with high-grade dysplasia, and 56 of the patients had no dysplasia. So it's pretty good results. And so this is now the basis for approval of this treatment in the US and Canada, and I'm not sure where else. Two controversies. One is, if you had this condition with no dysplasia, would you want to have PDT to treat the Barrett's? So, question number one. And the second question, which is also a big topic for conversation, is that there is one report in the literature where this treatment was given. The squamous mucosa regrew, and it looked great. But then it was found that this squamous mucosa had grown over a region of dysplasia and had hidden of the dysplasia. So there's a question as to whether this may actually be a little risky if there is incomplete destruction of the dysplasia.
What are the alternatives?
You have your esophagus removed.
Pardon?
You have your esophagus removed.
Okay.
And so if you have high-grade dysplasia, the standard of treatment is surgical resection of the esophagus. So Hugh Barr, it's interesting, there's a guy from England called Hugh Barr, who's a GI surgeon, very funny guy. And he and I were in a bar in Amsterdam a number of years ago, and he was a little drunk. So he was complaining about, this kind of situation that seems crazy. If I have a little spot of tumor on my hand here, the equivalent in the esophagus is I cut my arm off. So a little spot, not even a tumor, but a pre-tumor here, and you take your esophagus out. And the reason is that it's so dangerous to leave it there, because if it grows into carcinoma, that's uncurable. So this is the trade-off. There's another technique that's recently been introduced called endoscopic mucosal resection, where they use an argon plasma to completely strip the mucosa just by physical energy. And that may be competition for PDT. It does not require a drug. You can monitor exactly what's happening. The advantages of PDT, so just to summarize generally, can be applied locally to virtually any site. There's very little of those general toxicity if you compare this to chemotherapy, for example. You see that you can cure it in cases of early cancer. It can be curative therapy. It extends life and improves the quality of life in advanced cancer. Another thing that's not obvious is that it can be used alone or in combination with other therapies. And that's a big advantage. We're doing the treatment of the prostate with patients who've already had radiotherapy. You combine it with surgery. It doesn't matter if the patient has had chemotherapy or will have chemotherapy. It's easy to do can use PDT and there's no bad interaction between these. Probably that's because in the case of radiotherapy and chemotherapy, the radiation and the chemo are targeting the DNA, whereas PDT is not targeting the DNA, so you're hitting a different biological target. So you don't you don't have the additivity of the treatment. There's very good healing with normal tissues, and as far as we know, and this is a big advantage in principle, PDT can be repeated many times on the same tissue without causing either intolerance of the tissue or resistance. Again, because you're not changing the DNA, so there's no genetic alteration to the tissue, to the cells. So, for example, in the case of the prostate, the fact that we get incomplete response, it would be nicer if we got complete response, but we can wait for 6 months and then go in and treat again. And in the case of skin cancer, for example, some patients are treated as many as 6 or 8 times, just to control it. This is an example of the nice healing. So here's a tumor on the nose, treated with PDT. You see afterwards a very nice preservation, and that's because this is non-thermal, and so there's no destruction of the architecture of the tissue. Limitations. This is not as easy as radiation because there's a limited depth and volume of treatments. You can't put light here and get it to go through to the other side, so you have to worry about how to deliver the light. And it's complex. There's too many choices. If you give radiotherapy, one parameter to vary, how many rads. Here you have to worry about the drug, the time interval, the wavelength, how much light, and so on. So it's difficult to optimize PDT for clinically. And those are intrinsic. That's not going to change. There are other limitations that are really technological or knowledge limitations. The technologies are not fully mature. That's true of the drugs as well as the devices. The selectivity is not maximized. We have a couple of patients in our prostate trial where we have made holes in the rectum. We do not have complete selectivity. And there's been so far very limited tailoring of this to individual patients. It's tended to be as one formula fits all. So there's a lot of interesting research to be done by engineering people, chemists, biologists, and the computer people and measurement people. I just want to show this age-related macular degeneration. A little more details. This is where you have abnormal blood vessels growing in the back of the eye. I showed you this yesterday, the effect of this. The idea is that you give this region of abnormal blood vessels PDT treatment, and that's intended to destroy this abnormal without destroying the rest of the blood vessels. I showed you how that's done, and I showed you the examples. So here's before, and here's after. So basically, the treatment is closing down all these abnormal blood vessels. Actinic keratosis, just to give you an idea of what this looks like. Here's the blue light source. In this case, a drug, which is ALA, applied topically. This is a good example of medical engineering. So if you're going to give a topical treatment of a drug, and you're going to put the drug on the individual spots, how do you do that? Do you physician buy a bottle and take a piece of cotton wool? How would you actually design a system to deliver the drug just onto spots? That's not trivial. So it's very nice where they've done it. This is so-called peristate, in which the drug is inside a tube, this plastic tube, and inside here, the drug is inside a very thin glass tube. And so you just bend it, and the drug is released, and it comes out onto a cotton pad. So that's an incredibly well-designed piece of engineering. Very simple, works in all patients. You don't need to prepare, nobody handles the drug. You just have a little stick, ready to treat.
So what you say is, we have two compartments, and one has the delivery vehicle, and the other the drug.
Inside the glass, just crack, shake, put it on.
What about these pieces of glass? Does it go?
Well, you see, this is the cotton wool tip. So the drug just leaks out. You wedge the tip.
Oh my goodness. Yeah. Who makes this?
Juice-Up. The USA. It's on the list of Juice-Up pharmacy. And that's a result. Antimicrobial. Lots of interest in PDT as an anti-microorganism. Various possibilities: bacteria, fungi, yeast, viruses. Big challenge with respect to this is that unlike the mammalian cell, mammalian cell wall is pretty simple. It's just a sort of biolipid membrane. The bacterial cell wall is very complex and is very different for gram-positive and gram-negative. So you basically have a big challenge of how do you get the photosensitizer to go into the bacteria. And it's not even known where it has to kill the bacteria. Maybe you just kill the cell wall or destroy the cell wall. So just because a drug works in gram-negative does not mean that it will work in gram-positive or vice versa. Localized infections, for instance, periodontal or wounds. Implantable devices, for example, catheters that go into the body are a major source of infection. So people are making catheters or idea to make catheters that incorporate a photosensitizer and have a light source come into them so that it continuously self-sterilizes. The medical environment, there was a couple of companies studying making paint in walls there with photosensitizer. So you just paint the walls in the operating theater with a photosensitive paint, and it self-sterilizes. The operating room lights are bright enough, and so a bug lands, a bacterium lands, not a big bug, but a bacteria lands on the wall, and it's killed. Yeah, so that's really interesting. So all surfaces, operating surfaces.
How is the photosensitizer getting to the bacteria?
Well, the bacteria, it's not clear if it is. It may be that simply the photosensitizer is at the surface, the bacterium comes and sits on here, and the singlet option is generated in the surface and is enough to kill the bacterium by damaging the cell wall. You're not transferring the photosensitizer from the paint to the bacteria. It's just a singlet option generating surface.
Really that already.
Yeah.
So what you could do is you don't have to paint the wall, you can produce some little devices that has
Yeah, so there's lots of interesting environmental possibilities there.
What company is thinking about this?
There's a couple of companies that Photopharmaca, for instance, is looking at that. No one has done this. No one has a possibility. And it would apply not just to, you could think about it in sterile laboratories, not just to medical.
Professor, can it be intended for us in a very long
I don't think so, because well, I guess if you leaned against the wall. But I think
if you sleep against the wall.
Yeah, it's a good question, and obviously that's going to be a concern when this comes to approval. The other concern is that people have suggested, I should have added here, for water sterilization. So for sterilizing the water supply, where you would add a photosensitizer and then illuminate it with light. Things like this have two issues. Well, three issues. One, is it effective? Secondly, is it safe for the people in the environment? And thirdly, and probably the most difficult, is you then are subject to environmental waste disposal laws. So you have to prove that these materials are themselves environmentally safe. And that's actually quite difficult, because you want to have a material that is very photostable, that does not bleach. And if it does not bleach, how is it going to be destroyed for environmental disposal? So there's some real issues there. This just shows bacteria pre and post. These are E. coli, and basically the bacteria break up. You can do cell survival curves with bacteria. And you notice people are looking at logs of cell survival here. This is an example of PDT for wound healing for infected wounds, where in order to demonstrate that this is effective, the bacteria have been transfected with luciferase, so they're bioluminescent. And then this is each of the wounds, and this is the wound that has been treated, and you see there's much less bacteria there. This is periodontitis, where the idea would be that at the time of scaling, you would inject the drug or put the drug into the pockets. This is an example actually from our own lab of toyidine blue against P. gingivalis. If you look on the web, you will find a company, I'll show you in a moment, where they have diode laser delivering light into the pockets by an optical fiber. And they just reported a clinical trial of 600 sites and 33 patients with a greater than 6 millimeter depth. I guess this is pretty severe, right? Yes. 6 millimeter? I don't know very much sizes. This is severe, pretty deep. So the claim is that the pocket depth improved by 150% in 12 weeks. I'm not quite sure what improved by 150% means. But do you know, is that the standard way to report periodontal treatment? Percentage?
1.5 times better if you don't do anything.
I don't know what that means. Does that mean that they went to 4 millimeters? Or, I don't know. Anyway, maybe
Alfred's here.
Yeah, I think a more important statement, I believe, is he said they had got an attachment improvement in 12 weeks, and this was compared with scaling and replating only. If you want to look that up, this is by Ondine Biopharma. And on November 17th, which is 10 days ago, they got government approval in Canada on the basis of this data. So this is the first government approval for PDT for periodontitis. They call it a carrier wave. And very finally, I wanted to show one veterinary application. So this is PDT for canine osteosarcoma. This is not on your printout, I just put it there to show you. So this is a dog with osteosarcoma, so tumor in the bone. And this is MRI images. So what was done, I couldn't find the picture, but basically an optical fiber was put in percutaneously into the long bone, so this diffusing fiber along this length of tumor. And this is the MRI before treatment and the MRI after treatment. So it's you can produce a pretty big volume of killing. So now we're doing a trial on this with people at University of California, Davis, Veterinary College. So if you're interested in that, it used to be a pretty...
So the fiber goes inside the bone?
Yeah, we actually put it into the medulla. So we just make a little drill hole and the fiber goes down, the length of the bone, delivers the light, and all that. So this initial study was done in dogs who were slated for amputation. We have the post-histology, but now the trial is just starting to try to save the life. Interesting application. Okay, one finish. I'm sorry this is taking so long. I'll give you things. So all this has been about how great PDT is, right? So you're all convinced that PDT is a great thing to do.
Oh, you are convinced.
Right. So let me show you one case that tells you this is not so easy. So this is the first patient we treated with PDT. A gentleman with big recurrent nasopharyngeal cancer. Big mess. This man was in big trouble. This tumor was invading into this skull and everything. So we gave him photoprint, delivered the light, lots and lots and lots of light, lots of drug, absolutely zero happens. Zilch. Nothing. And so, why? Well, this was 20 years ago, so we didn't have any of these measurements. We just thought, well, we'll give the treatment and it'll work. So I just posed to you to think about why would this treatment have failed? Did we not get enough light? So now we would measure the light, so we would be able to answer that. Was there enough photosensitizer? There was lots of blood. It's a very bloody tumor, so there's lots of vasculature, so there should have been lots of photosensitizer. Did we use the best drug time interval? Maybe the pharmacokinetics in this guy were crazy. He had lots and lots of treatments, maybe just crazy pharmacokinetics. Maybe this tumor didn't care. And for some reason, you could not kill this type of tumor with photoprint-based PDT. So I just put it to you as an interesting case where...
It's hard to believe in this question because you have vessels and you always have vascular damage.
Yeah.
So something should happen.
So this gentleman, nothing. Zero. The next lady we treated was a lady with big tumor on the chest wall, recurrent breast cancer, about this size. We could not go fiber in. Exactly the same drug, same amount of light, gave the treatment, she came back the next day and the tumor had collapsed. So, it's not so easy. So, I'm sorry that took a long time today, but I wanted to finish the PDT part. We'll have a short session tomorrow. Thank you. So if anyone wants to